Alright, welcome to the last video for this section. And we're just going to go over just some brief vocabulary, some definitions, and then we're going to look at a few solutions, how to check for solutions and see if it's linearly dependent or independent. Alright, so we're going to let t sub 0 denote a point on the interval I and x of t sub 0 equal, and so then we have pretty much our solution matrix, and x sub 0 is equal to gamma 1, gamma 2, so a matrix filled with gammas where our gammas are going to denote our given constants. Then our matrix C we can write as solve x prime is equal to a of t of x plus f of t, subject to x of t sub 0 is equal to x of t. So if we ever have that, what we're going to have is we're going to be given an initial value problem on the interval. So we're going to let the entries of matrices a of t and f of t be function continuous on common interval I that contains the point t sub 0. Then there exists a unique solution of the initial value problem on the interval. So basically what this is saying is that if we are given initial values, we're going to be given an initial value problem where this denotes, hey, you have initial values. So we can have a unique solution given the initial value. So instead of solving and having a family of solutions, once you're given an initial value, you're going to have a unique solution. Now, the superposition principle that we've had, in the past still holds true now, that if we have, all these solutions to our, differential equations, then we're going to combine these together to write our, solution to the differential equation. So that's just the superposition principle where we combine all of our solutions, where c sub 1 and c sub 2, these are just constants in front of each solution. All right, now, also, we want to find out something's linear dependent or independent. So let x sub 1, x sub 2, x sub k, so all of our solutions be a solution vector of the homogeneous system on interval I. We say that the set is linearly dependent on the interval if there contains c sub 1, c sub 2, c sub k, not all zeros, such that c sub 1, x sub 1 plus c sub 2, x 2 plus all the way to x sub k is equal to 0 for every t on the interval. Otherwise, the set is called linearly independent. So what we're going to do is we're going to check to see if a solution is linearly independent or not. And so we can use the Wronskian. The set of solution vectors is linearly independent on I if and only if the Wronskian does not equal 0 for every t in the interval. So we're going to go back to the Wronskian to see if something's linear independent, dependent, just like we did in past chapters. So any set of n linearly independent solution vectors of the homogeneous system is said to be a fundamental set of solutions on the interval. And so our general solution would just be that superposition principle where we combine all of our solutions, making sure that we provide the correct constants in front. So example 3. The given vectors are solutions of a system. Determine whether the vectors form a fundamental set on the interval. So here again we denote that, hey, we have a homogeneous because we have that, we don't have that plus f of t. And now let's go ahead and check to see if this is going to be a linearly independent or dependent solution. So we're going to take our two solutions, x sub 1 and x sub 2, and I'm gonna write those down. I'm gonna first write those in matrix form. So again, all I did was multiply the scalars and combine them. All right, and then I wrote out the solutions for that first one, and then the solution for the second. And now what I'm going to do is go ahead and take the Wronskian and multiply e to t times 6 e to the t minus 8t e to the t. And we get 6 e to the t minus 8t e to the t. Then we're going to take the other two. So remember, we're going to minus, and then we're going to minus the second part. 2e to the t plus 8t to the t times negative e to the t, which is negative 2e to the t, negative 2e to the 2t minus 8t e to the 2t. Don't forget to distribute that minus sign When we do that, we get 8e to the 2t, which is not equal to 0, so the set is linearly independent. Alright, the last example is when we're dealing with a non-homogeneous system. So let x sub p, so that particular solution, be a particular solution of the non-homogeneous system, and let x of c be the general solution of the associated homogeneous system. Then the solution of the non-homogeneous system is x equals x to the p plus x sub c. So again, nothing different than past chapters. We're gonna have the combination to have the general solution. And so example 3, verify that the vector x of p is a particular solution of the given system. So again, we're just doing the same thing. We're going to go ahead and take our, so here is our solution vector that they, or not vector, but solution matrix that they gave us. Let's take the derivative. So we take the derivative, we get 0, 0. All right, so now we're going to set that over here to the right and on the left. And now on the right, what we're going to do is we're just going to go ahead and plug in. We're going to plug in this x of p into that x. So we're going to have 2, 1, 1, negative 1 times x, which is 1/3, or sorry, 1, 3. And then we're going to, add negative 5 too. And then now we're just doing matrix operations. Multiply, right? It's a 2 by 2. This is a 2 by 2 times a 2 by 1. So the middle checks out, and we're going to get a 2 by 1. And so we get 2 plus 3, 1 minus 3, which is going to be 5, negative 2. After we do the multiplication, we're going to add that to negative 5 too. We do the math, we get 0, 0. So yes, x of p is a solution. And that's it for this section. And then we'll start to actually get to more solving these systems of linear differential equations tomorrow.